In this video, we'll take a look at concepts from section 6.1 and 6.2, and it's all about factoring. In section 6.1, we're going to factor the greatest common factor and also take a look at a difference of squares. So what factoring is basically going backwards from the distributive property. So if we take a look, greatest common factor ax plus ay is equal to factor out what's common in both. So a times x plus y. So factors mean we're going to take an expression and rewrite it as a product. So instead of ax plus ay, we're rewriting it as the product of a times parentheses x plus y. So the greatest common factor, next example, so we're going backwards from what we did the first week of class. We multiplied things out, and now we're taking them and rewriting them as products. All right, so when you factor out a greatest common factor, you take a look at both terms and see what is common to both. If you take a look at the numbers, we have 4 and 2. We want the number that goes into both 4 and 2, which is 2. Then we take a look at variables. We have a and another a. They're both to the power of 1, so they both share a to the power of 1. Now we take a look, they both have an x. This is x squared and x. The least, or the number that goes into both, pick the one with the smallest exponent, is x. So now what we're going to do is we're going to go and divide each term by 2ax and see what's left, and that's what goes in the parentheses. So if I take 4ax squared and divide by 2ax, 4 divided by 2 is 2. A divided by a cancel each other out. X squared divided by x is x. If I divide the second term by 2ax, notice they're the same. Anything divided by itself is 1. Now you can check your work by going the other direction. If we multiply these out like we did when we multiplied polynomials, we get 2ax times 2x plus 2ax times 1. We end up with 4ax squared plus 2ax. That works. It checks with our original. So that's factoring. Greatest common factor is find what is the largest factor common to all your terms, divide them out, and rewrite it as a product. Okay. So next example, we have 3 terms. So we take a look at the numbers first. We have a 6, a 9, and a 3. What will go into all of those? 3 is the number that will go into all of them. Then we take a look at our powers of a to the 5th, a to the 3rd, a to the 3rd. A to the 3rd is the greatest power that will go into all 3. And then x squared, cubed, squared. X to the power of 2 is the greatest power that will go into all 3. Then we're going to think about this a little bit different. If you don't like the dividing, think about 3a to the 3rd x squared times what would equal 6a to the 5th x squared. Okay? So you can think about it either way. What do I have to multiply by or divide them? So the first I get 6 divided by 3, which is 2. A to the 5th divided by a to the 3rd, subtract the powers, is a squared. The x squared divided by x squared is 1. Next term, divide. 9 divided by 3 is 3. A to the 3rd divided by a to the 3rd is 1. X to the 3rd divided by x squared is x. Last term, these terms are exactly the same, but it doesn't mean we don't put anything there, because anything divided by itself is 1. All right, the next factoring technique in this section is a difference of squares. So when we've multiplied out a plus b times a minus b, just a reminder, let me think, it's something like x plus 2 times x minus 2. When you multiply these together and they're in this form, you end up with x squared plus 2x minus 2x minus 4. The two middle terms cancel and you're left with x squared minus 4. So when we're starting with the expression x squared minus 4 and we want to go backwards and rewrite it as a product, then we recognize that your first term is a perfect square, it's x. Your second term is a perfect square, 2. And when we go backwards, we rewrite that as the pattern a plus b times a minus b. So let's take a look at our examples. We've got factoring x squared minus 16. Is this a difference of squares? And the answer is yes. X is a perfect square, x squared is a perfect square, and 16 is a perfect square. It's 4 squared. So the x and the 4 are our a and b in the pattern in the formula. So that factors into x plus 4 times x minus 4. Okay, so next example, factoring completely. So sometimes you'll have not only greatest common factor, but you might also have difference of squares all in the same problem. So notice this is a difference, but these aren't perfect squares. 20 and 45 are not perfect squares. So what we always look for in a factoring problem is there a greatest common factor first? So we have a note, oh, there's a 5 in each term. So we're going to divide out or factor out of 5 first. So 20 divided by 5 would leave us with 4x squared minus 45 divided by 5 is 9. Then what we have left is a difference of 2 squares. The first one, the 4x, is 2x squared. The next one, 9, is a perfect square. That's 3 squared. So now we can factor again. That factors into 2x plus 3, 2x minus 3. So factoring completely means take out the greatest common factor first and see if you can factor what's left. Okay. Next example, we have x to the 4th minus y to the 4th. They do not have a common factor, but they're both perfect squares. X to the 4th is x squared squared. Y to the 4th is y squared squared. So difference of squares factors into x squared plus y squared, x squared minus y squared. Okay, last example is, again, we have a situation, 45 capital R squared minus 20 small case r squared. And when in factoring this expression, notice the factor happens to be a 5 again. Factor out of 5, we're left with 9 times capital R squared. 20 divided by 5 is 4 small case r squared. This is a difference of squares. 9r squared, the perfect square, is 3 capital R plus 2 small case r, 3 capital R minus 2 small case r.